Saxon Advanced Mathematics, Lesson 34. Today is a lesson designed to make you feel smart. I promise you. 3 topics. All of them are fairly digestible, but they're all going to make you feel smart. The first one is called summation notation. It's something new. It's something we've never done before. We're not going to complicate it or make it too much worse. So what you see is what you get, but it's going to make you feel really smart. Summation notation is the idea that sometimes we're trying to add together a lot of numbers that fit a pattern. It's for adding. Summation always implies adding. And there's a really simple, there's a really cool code that we use for writing it down. The base of that code is a Greek letter. It's called sigma. Okay, so that's how we say this. That's sigma. And then there are little numbers floating around it. What we do is at the bottom we write something like this, y equals 1. This is what we call the variable of summation. That sounds really fancy. Don't worry, it's not hard. Up here, we have what we call the greatest value. And then written here to the right of the sigma is what we call a typical element. Let me break that down for you and tell you in simple English what it is that we're doing. What this is saying is take this number, plug it into this expression, find the answer, then add it to the next number in that expression, then the next number all the way up till 4. So here's how we would do that. We would take 1, that's our first variable of summation. We square it because that's what that tells us to do. And then we add it to the next number after this, 2 squared plus 3 squared, and we go all the way up to and including 4 squared. That means this. And then all we have to do to finish it is do those calculations and add it all up. Oh, I want to just tell you this. We call this the value of summation, this y equals 1, but it's also the least value. Okay, that's where we start, right? We started with 1, we went all the way up to 4. We're just doing counting numbers. There's no fancy fractions or anything. And we're putting each number into this function is a way of thinking of it. So this becomes 1 plus 4 plus 9 plus 16. And we add it all together, it's 30. The calculation is fun. The only complicated part of this is just cracking the code, right? So here's another one just for practice, and then we'll get into some examples. Drawing these is just the most fun of the whole thing. I equals 2. And then our typical element is I times K. That's weird. And then this says 5 up here. So this tells us start with 2, plug it into this, keep going all the way up till 5, add all those different pieces together. All right, so we're just plugging 2 in, so it would be 2K plus 3K plus 4K plus 5K. We include this number. I used to get confused. Does it mean don't include 5 or do include 5? It means do include 5. We add them all up and we get 5, 10, 14K. Okay? So the moral of this story is you can do it where your answer turns out to be all numbers, but you can do it where you have letters too. That's fine. Right? And I will mention again, I don't know if I've said this kind of calculation is usually part of a bigger problem. Honestly, you can assume that really for everything that we do, it will eventually come into play in a larger problem, and this will just be one step. So John's baby stepping us through so that we understand. All right, let's do just a couple more. Those technically weren't examples. I don't know what John's thinking sometimes. Why is that not an example, but this, which is exactly the same, is? I like to make my sigmas really big just because I think it's fun. You don't have to. All right, I equals 1. And our typical element is 3. And we go all the way up till 5. Okay, now this looks really confusing because there's nothing, there's no I in this equation. So what we can do is remember that I to the 0 equals 1. And we can see this as 3 times I to the 0. Now we have something we can plug our I into, but as you'll soon see, it doesn't do us any good because our first element would be 3 times 1 to the 0, and then we would add 3 times 2 to the 0, right? So we're plugging all these values of I into the equation. But here's the problem. All of these I values raised to the 0 power are all just going to be 1. So in the end, we just have 3 times 3 times 3 times 3 times 3, or plus rather, sorry. 3 plus 3 plus 3 plus 3 plus 3, and that equals 15. And that's the right answer. Now, why you would want to set this up as a summation problem makes no sense, but that's an easy enough answer, right? 34.2. Here we go. X equals 1. We go all the way up to 4. And our typical element is 2 times x. All right. These are pretty easy. We're going to get relatively more complicated elements here before too much longer. All right, so this equals 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. And that will be 2 plus 4 plus 6 plus 8. And that equals 20. Okay, so we're going to continue this. Now you have a sense of how the pieces fit together. We're going to make our typical elements a little bit more complicated. All right, this one was weird, but we're just going to kind of up the game a little in that direction. And this is example 34.3. And here we've got J equals 0. I usually write them in this order. I write the starting element, and then I write the typical element, and then I write the greatest value up there. All right, so we only have to go from 0 to 3. That's pretty good. And I'm going to write my values down here because they're complicated enough I don't want to squish them. So let's start with 0. 2 to the 0 power over 0 plus 1. Whew, I'm glad to see that plus 1 because that scared me to write a 0 down there. Next one would be 2 to the first power over 1 plus 1. Okay, so you can see the process is the same, but this is a little more complicated, isn't it? And then 2 to the second power over 2 plus 1, And then our last value is 2 to the third power over 3 plus 1. Now I just have to simplify all of this and add it together. So 2 to the 0 power is 1 over 1, plus 2 to the first power is 2 over 2. 2 squared is 4, 2 plus 1 is 3, and 2/3, that's 2 times 2 times 2, that's 8 over 4. Now that looks like a lot of hideous and scary fractions, and it kind of is, but look what happens. This is equal to 1, this is equal to 1, this is equal to 2. So my final answer is 1, 2, 3, 4 plus 4/3. So there's a couple ways I could write that. I could write that as 5 and 1/3, but you know how I feel about mixed numbers. So we could multiply this by 3 over 3 and make it 12 over 3, and then add this, and I would get 16 over 3, which you would agree is the same, right? 15 plus 1 is 16. So I like this answer the best, but I would not take any points away for that one. That's fine too. Okay, so this gives you an example of how these elements can get a wee bit more complicated. And here's, I think this is our last, yeah, this is our last example on this topic. 34.4. We start with y equals 4. Our typical element is 1 over y, and we're going to go up to 6. Okay, so that means we only have to do 4, 5, and 6. So it's going to be 1 over 4 plus 1 over 5 plus 1 over 6. Now, that's not a particularly complicated arrangement there, but now we have to make all those denominators match. What's the least common multiple here? Well, let's see. I'm going to do this by prime factors. This is 2 times 2. This is just 5, right? And this is 3 times 2. So my least common multiple has to be 2 times 2 times 3 times 5, which equals 60. All right, so this is how we can use prime factors really easily to find least common denominators. So, and it's helpful too because like this one, okay, I've got a 4. So what do I have to multiply? Well, I can see there's the 4, and so I have to multiply it by 15 over 15. Here's the 5, so I'm going to have to multiply it by 12 over 12. And here's 6, so I'm going to have to multiply it by 10 over 10. Using the pieces of the least common denominator or least common multiple can make it really easy for you to come up with these fractions because you just look at, okay, which piece do I have, and that's the other piece I need. All right, so now we've got 15 plus 12 plus 10 all over 60. And then I just add those little puppies together. And that equals 37 over 60. 37 is prime. So there's my final answer. So this was an example where creating the elements was pretty easy, but the simplification kind of dragged us down a little, didn't it? Obviously, this is all done by computers, and a lot of calculators can even be programmed at this level. But that's why we don't use calculators. I want you to learn the concepts and the reason behind everything, and then later you can learn how to push the buttons, right? That's not hard, but it's important that you learn what it all means before you get into that. Okay, that's topic 1. Topic 2 is going to annoy you, but I promise you it's going to make you feel smart. I'm going to show you the picture first, and you're going to go, oh, please. See what I mean? We're doing this thing again. But here's the thing. It has a new name. It's called linear regression. And that is fancy and legitimate sounding. And so I want you to have a new pride in these. This is another example of a problem that can all be done on a calculator. And when you get to college math, not college level math, because this is college level math, but when you actually get to taking this in college, your professors will undoubtedly have you solving these on a graphing calculator, which is cool. But I'll tell you what happens to everyone, including me, including those faculty. As soon as you put that calculator in your hand, you stop thinking about the math and you start thinking about, oh, but wait, what buttons do I push? All the math goes flying out your ears, and all you're thinking about is, how do I push the buttons to get the right answer? It's so important to learn the concept first, and later you can learn how to push the buttons. Okay, now here's the deal. It says the data points, let me show it to you again. These are exactly the same as what we did last year. We just have a better name. And this is a really good graph, so don't be mad. Okay, the data points from an experiment involving carbon and salt are given here. Okay, so here's the carbon that we put into the experiment, and here's the salt that we got out. And here it is plotted. This is the same graph. This is before they drew a line, and this is after, so you can look at either one. So the person doing this experiment plotted all of these points and then decided that a line went through about there. I want to tell you this. If you're using a graphing calculator, what you do is you simply enter in all these points, and then the calculator will graph them for you and give you a line that goes through them. So that's cool. In our case, the scientist drew the line, and we're just running his numbers for him. We're just going to find the equation of this line for him. Now, whoever drew this line did a really big favor for us, because look how this first point is spot on. It's 40 and 0, right? And then up here, it's also spot on. It's 160 and 10. So they did a really good job, and we're going to be able to use these 2 points to find the equation of our line, and it's going to be beautiful. So let me just remind you how we do that. This is example 34.5. It is getting dark so early, right? So the first step is find 2 points. And I'm going to write 2 perfect points. And by that I mean we want them to hit the corners of the graph paper, so to speak, right? And we found 40, 0, and what was it, 160, 10, I believe. Right? I showed them to you. All right. Then the next step is we're going to use the points to find the slope. And remember what we're going for here, what linear regression always means is we're trying to find the equation of the line. It's just a fancy way of saying that. We're working backwards from points to the equation. In order to use the points to find the slope, we need that cool slope formula. M equals y2 minus y1 over x2 minus x1. And in this case, remember to use buckets for this, because there's minus signs in the formula, and there can be minus signs in the points. So that's just crazy. And I always like to do this, x1, y1, x2, y2. So y2 is 10, y1 is 0, x2 is 160, y1 is 40. Remember, it doesn't matter which pair are the 1s or the 2s. I just did it in order, but it doesn't matter because it'll work out either way. The minus signs will sort themselves out. Okay, so this is going to be, I'm going to write it on the next page, but our slope is going to be equal to 10 over 120, right? Gracie's sitting directly underneath my feet. So, M equals 10 over 120, which we could reduce to 1 over 12. And that's fine. That would be my preference. But remember that scientists always would rather have decimals than fractions. They're just that way. And so we can convert this to a decimal. And I don't want to take the time to do the side calculation. And I do not want you to do your calculators. Remember, we do not use calculators unless I specifically say so. We do not use them to do simple calculations like this. We do them by hand because it keeps us sharp. Okay, now we have a very nice slope for us to use. The third step is to use one pair of points and remember that's going to be x and y and our m to solve for b. Right? Because we're working off y equals mx plus b. There's our m. And let's see, we'll use, I remember the first point was 40, 0, right? So let's plug those in. 0 equals 0.083 times x, which is 40, plus b. Right? Do you remember doing these last year? We did them for a long time. It's the same exact work. It's just called linear regression. All right, so we need to multiply that 0.083 times 40. Remember when we're multiplying by a number that has zeros, we can just kind of hang it off the edge, copy it down, and then multiply from there. 2, that's 33. That carried, and then one more 0, don't really need it. And then how many digits behind? 1, 2, 3. 1, 2, 3. So this number actually equals 3.32. So we're going to subtract 3.32 from both sides. That will get our b by itself, and we'll get minus 3.32 equals b. So for our final answer, we will write y equals m x plus b, which is actually a minus 3.32. But then at the very last, remember, we go, oh yeah, this was about carbon and salt or something, right? So I just look at the book to make sure I've got the right letters. Yeah, it starts with carbon and it ends with salt. So we put the S in for that one. 0.083 times the carbon. The carbon is on the x-axis, the salt is on the y-axis. You just copy. Minus 3.32, and this, yay, is the right answer. Beautiful. Okay, again, remember with these problems, it all comes down to finding perfect points. As long as we can find them, these problems are quite easy and straightforward. But now they're called linear regression. Feel smart. Okay, the third topic for today is called decomposing functions. That does not sound cute. I don't know if you care about your math topics being cute or not, but that sounds disgusting. That sounds like something that's happening in my compost pile. Functions. And at first, anything with functions usually makes students go, ah, but you'll see, this is not hard, it's easy and fun. Okay, well, I think it is, but I think it's all fun, pretty much, except those stupid parallelogram properties. I don't like that at all. Those are dumb. Okay, find two functions, f and g, such that f combined with g, that's how you say that, of x equals the square root of x squared plus 1. Okay, so what this is saying, remember this sign means combined with, but we can say it as eats, right? what we could do is we're trying to think of what these were originally, that when they got shoved together, they ended up being like this. So what we can see is that maybe the f function was, take the square root of x, and then the g function was x squared plus 1, right? Because then when f8g, this would go inside of it and end up like that. So this is one acceptable answer, okay? Another option would be, what if it started out and then the g function was x squared? Then we would put the x squared in there, and that's another way we could get that. The third way, oh wait, before I go on, let me tell you what I would call both of these. These are called non-trivial compositions. Decompositions. Sorry for the hyphen there. They're called non-trivial because they're both like cool functions. What would be considered a trivial function is, we said, oh, let's just let the f of x equal x squared plus 1, and then the g of x, we'll just say that equals x. Because then when this goes in there, it's exactly the same, right? That's kind of cheating. I mean, it's not cheating. It's kind of like, 17 only equals 17 times 1. This is called a trivial function because it's not very interesting, right? It's just plain. The other trivial function would be if we said f of x equals, just plain x, and then the g of x equals square root of x squared plus 1. These are boring because it's like multiplying by 1. That's the best way I can say it. So when we're answering these questions, we're looking for what are considered non-trivial decompositions because they're more interesting. And once you get the hang of these, most students find them kind of fun. Let's do another one. These are obvious, and they involve one of them, either the f or the g, but they involve one of them just being a plain x. Okay, here it was the g, here it was the f. It doesn't matter which one, but one of them is just plain x. And these are not so obvious. And that's what most students like about them, is you kind of have to think for a minute and pull them apart. All right, and the last problem for this lesson, thank goodness, finally, I think is even more interesting than the last time. The last kind of problem. It says find f where g of x equals x squared plus 1 and f combined g of x equals 1 over x squared plus 1. Remember, we say this as combined, f combined with g, but I always think it as eats, f eats g. Okay, so if this is g, then what would the f function have to be so that when f ate g, it went down here? Well, somehow we need to send this to the denominator. So consider that. If this was the start and then it ate this, it would plug this in wherever there was an x, and so that would become x squared plus 1 on the bottom, and that's exactly what we're going for. So these problems do not require calculation per se, but they require a few minutes of thought about how would you take this one and get it to look like this is the combined function. Most students find these a little bit easier because you have kind of like more clues, right? You know this is where you want to end up, and you know this is part of it. And then you have to figure out, all right, what would the other function have to be so that when this one eats this one, you end up with that. Hopefully you can see it. This is one of those things that's kind of hard to teach. You either just see it or you don't. That's the end of lesson 34. I hope that you do feel very smart and you are ready to tackle this lovely homework. We still have concept review problems and you're still skipping them. Right? Right. Okay. Good job. Thank you. Goodbye.